Hi, everybody. Thank you for joining. I'm Taro. I'm going to show how to maximize the power of Scala, both for front-end and back-end development. A little bit about me. I'm principal software engineer of Treasure Data. At my work, I'm building distributed query engine services for our customers. And I've been using Scala almost for 13 years since Scala 2.7, which was released around 2008. I built Airframe, which will be explained in this talk, which also has 20 or more Scala utility modules. And also I have created SBT stone type. You might have used this one for publishing your Scala project into Maven Central. A little bit about my work. Treasure Data is actually providing a ready-to-use cloud data platform. So even if you are not an engineer, you can start collecting your data and analyzing your data. We have created many open source libraries for collecting your data, like FluentBit, FluentD, which are also used for internal logging or Kubernetes. We also created Embark for bulk data collection. Then once your data is stored on our cloud-side data platform, you can make query against using other open source technology like Trino, SQL, distributed query engine, or Hive, or Apache Spark. You can also organize your SQL job using DigDag, another open source from Treasure Data, for organizing complex data workflows. But my work is mostly building backend side work, but database systems or data storage, but even backend engineers like me sometimes need to create front-end applications, like creating a better visualization of our services. Especially in Treasure Data, we are running millions of queries every day. So simply looking at individual query logs is almost impossible. So we need a better UI for navigating individual queries and seeing the history. We created this kind of UI for service monitoring and cluster management by using Scala.js, which is running on web browsers. We also created another Scala.js application, like Notebook Query Editor, which is integrating Scala.js and the Monaco editor, which is actually from Visual Studio Code's editor. Then you can build a nice, rich SQL editor running on your web browsers. And the backend side is using Scala running on JVM, which also has RPC server for running SQL queries and managing fine-grained tasks. These applications are totally written only by using Scala. But in reality, if you need to write both front-end and back-end applications, you encounter a lot of frameworks existing in the world. If you know about front-end frameworks, you might have heard about React by Facebook or Vue.js. You might also know Electron for building desktop application using web browser technologies. You might need to use TypeScript, Bootstrap, CSS library, jQuery. There are many frameworks, even for front-end. Backend also has many frameworks. Like for Scala, there are Akka, Play Framework, Finagle by Twitter. You may also use Netty, Spring, Jetty. These are from Java framework. So then too many things to learn. So you can't make a choice which framework to use. And also it's almost impossible to find Scala engineers mastering all of these technologies. So how do we address this issue? Our solution so far is creating an Airframe RPC, which is using plain Scala as an RPC interface between front-end and back-end applications. So once you define Scala interface using Scala trait and define some function, you should be able to use this method for communicating between front-end application and server-side application. Actually, this is once we created RPC, Airframe RPC, it will require really low learning cost. because it only requires basic Scala knowledge, how to define function in Scala, how to define case classes in Scala. This thing just can be learned by reading one Scala book, like Programming in Scala, written by Martin Lasky. This Scala book is really a comprehensive guide of learning Scala. Our experience so far after introducing Airframe RPC is, for example, a Java engineer who didn't know much about Scala could start writing Scala RPC services, interacting with the Scala.js UI just in a week. This was so impressive. So it significantly reduced the learning cost of writing front-end and back-end applications. Then first of all, what is Airframe? Airframe is an open source library which contains 20 or more useful modules written in almost pure Scala, which is also cross-built for Scala 2.12, 2.13, and Scala.js. Scala 3 support is also in progress. I think it's almost 85% completed, which is talked in this GitHub issue ticket. There are several work in progress, things like supporting compatibility layer between TXT reader in Scala 3 and Scala 2 reflection. Airframe basically has several core modules like Airframe log for logging your application code, or airframe-codec is also for serializing objects. Airframe HTTP, which will be explained in this talk, has RPC support. And Airframe RX is used for rendering DOM object for your web browsers. There are a lot of other useful libraries, including AirSpec testing library, which are integrated with another library in Airframe, like Airframe DI, dependency injection library for supporting constructor injections. But before building Airframe, which was 5 years ago in 2016, our Scala technology stack was a sort of mess because we were running business. We created a lot of code, but our code base are using various internal and third-party libraries, both in Java and Scala. Many web frameworks were used. There are many utility libraries are used. So as we running a business, we learned a lot of things, but our code base is becoming a lot of technical debt. And also the cost of learning individual library usage became significantly high at that time. So we tried to solve this problem by consolidating our standard or best practice into a single Airframe OSS library. And in 2016, we started defining some standards in Airframe so that engineers can focus on developing applications instead of learning individual frameworks or making choices about between frameworks. One of the examples we simplified our use cases is Airframe log. This is a library for human readable logs, which can be used both for Scala JVM and Scala.js. Actually, the problem solved by Airframe log was that there were too many choices just for producing human readable logs, like log4j, SL4j, Scala logging, Java UT logging, and Twitter UTs logging. So there are too many logger libraries, even for Scala. But what we really needed was just for showing colorful logs with a source code location like this screen. So Airframe log usage is quite simple. You just need to add log support trait to your class. Then you can use info or one debug log methods so that you can see this kind of colorful logging with source code location information. That is super useful. You might have seen this kind of log message if you are using sbt-airframe for publishing your project to Maven Central. It actually shows the detailed publishing step to the Maven Central. This is a little bit off topic. I want to let you know a recent update of sbt-airframe. Since 2019, sbt-airframe introduced a new so-called bundle upload process, which can upload thousands of artifact files in a second, in a minute. For example, this log shows the publishing state of Airframe itself. Airframe has more than 3,000 artifact files because it has 20 or more modules, and it's also cross-built for different Scala versions. So previously, publishing Airframe required 2 or 3 hours just for uploading artifact files to Sontime. But using bundle upload, we can upload the entire 3,000 files within 20 to 30 seconds. It's blazingly fast. So if we didn't know about this feature, you should use it. Then, Airframe log is also useful for logging at your web browsers. And actually, Scala.js compiles your Scala code into JavaScript, which runs on your web browsers. Then you can see the same login message by opening the developer console of your web browsers. So if you like this kind of login code, you can see the log message like this. So what do we need for front-end development, in fact? Actually, what we need is very simple. We just need to render DOM object with Scala.js. DOM element basically consists of 3 things: tag, and attributes like class equals to container, and its enclosed elements. Then, there are a previous approach for rendering DOMs using Scala's XML literal for building DOM tree nodes. Like there are several open source libraries like Monolith HTML, Binding.Scala. This approach is very similar to JSX, if you know about the Facebook React, which is actually embedding XML syntax into JavaScript code. So this XML document is actually a valid Scala syntax in Scala 2, but this XML literal support will be deprecated in Scala 3. So we need another approach. But you don't need to worry about it because Scala is so powerful, and you can define DOM elements just by using Scala functions. So the kind of best practice is defining function for rendering HTML element or individual HTML tags like HTML, body, div tag, span tag. These tags can be defined as Scala functions. Then you need to compose these functions to build complex nested DOM elements. And for doing so, Scala has 2 major streams. One is separating DOM attributes and elements into different blocks, like in Scala tags. This example, upper part of this code is example of Scala tags, which, for example, H1 element had 2 blocks. One is for embedding DOM attributes like CSS styles. The next block is for embedding text elements, child elements. But this approach has some disadvantage, like you need to write many parentheses in your code. And so it's a little bit annoying for Scala format linter to create a well-nested structure in your editor. So there is a little bit better approach, like style 2, enclosing both DOM attributes and elements inside a single function block. So this approach is taken by Airframe RX and Scala.js React. So for example, H1 element now has both CSS style and text element inside a single parent. This approach actually makes clear the beginning and end of tags. So this is actually a much more Scala-friendly approach. So you can use Airframe RX, which is a library for building DOMs. Then to define more complex element, you can extend RX element, which has a render method, which generates DOM elements like this. So this new button function creates a button with event handler, mouse event handler. Once this button is clicked, it shows a alert window on your web browser. Then you can use this function, for example, changing the text label of the button or adding more custom style to the button to show, for example, bold label. If you need to build more complex user interface like this shows actually a list of jobs running on the system. Then you can create a table like here. Table header is written here. Table body can be written by iterating over the list of table row elements, so that you can customize the visualization for each row by iterating over the list of table of contents. If you are building front application, you will notice you need more reactive implementation or reactive event handling support, like you need to receive mouse click events or getting RPC response using Scala future or running interval timers or running something periodically every second, every minute. But you can use a reactive stream interface for writing such code, and which is actually almost the same with using Scala collection API like map, flat map, filter. Simply, the difference is you are continuously getting an event from upstream operators. Additional functionality you will need is some sort of variable support. Rx variable will fire an event if the variable content is updated. For example, if you can define a variable with a text string world here, then you can chain a map operator to create a new string hello world. Then you need to subscribe this Rx operator to get a new response, then print a message like hello world. If you set a new variable content, then this map operator will be re-evaluated, then produce the next updated string, hello Alex. Then once you, this is super useful for updating DOMs for each event. But after switching the page, web page, or after the DOM becomes unnecessary, you need to clean up the event. So having a cancelable interface is super important, so that you can clean up unnecessary event handle, mouse click handlers, timers after finishing the subscription, after calling the cancel. Airframe RX has this kind of cancellation support. You can find more example in GitHub repository. Airframe RX has a gallery for example, this source code generate this button UI. You can also customize the CSS. You can also create colorful buttons by just adding class elements. And also, it's also possible to render SVG vectorized graphics using SVG tags. And also, you can also subscribe timer, which is running every 1 second, then update the DOM element. So next step is, so now you are ready to create UI by using Scala.js. The next step is how to interact your Scala.js application with server-side application written in Scala. Ideally, if we call some function inside Scala.js, then getting a response from the server side, it's very ideal. But in reality, however, we need to make a remote procedure called RPC, which will translate your Scala object into some binary format so that we can send the object data through the network. Then at the server side, you need to deserialize so that you can get the original Scala object. Then running a function call, and the return response also need to be serialized again so that you can send the return response to the client through the network. So there are many things we need to consider behind the scene. Traditional approaches for implementing RPC include two major things, like building REST API or using gRPC. For REST API, you need to define function interfaces by defining some HTTP endpoints like get methods, post methods, delete methods, and so on. There are many REST frameworks for Scala as well, like Play framework, Akka HTTP, network fin, Skinny framework. You can use whatever frameworks for building REST API. If you want to use gRPC, which is based on HTTP2 protocol for low latency interaction, you need to use Google's ProtocolBuffers schema language to define RPC interface or define ProtocolBuffer objects so that you can send the data through the binary format. Then you need to generate server and client code stubs from proto files. Scala also has some gRPC workparts like Scala PB, mu Scala, Akka gRPC. So you need to learn additional things about Scala. But do we really need to learn additional languages like REST or gRPC? Actually, our take is different. We don't need to introduce new language just for building front-end and back-end application in Scala. We just need to use Scala interface as is for defining RPC interface. Actually, Scala is a perfect fit for RPC because Scala functions can be just RPC methods, and Scala objects which are statically typed can be RPC request and response types. So we should be able to use the same interface and model classes between server and client code. Then if you can use this approach, you don't need to think about any REST nor protocol buffers for implementing RPCs in Scala. So behind the scene, we need to implement several things to make this approach possible. First is we need to serialize a message so that we can send the data through the network. We also need to define the network data format we are going to use. If we are using REST framework, it should be JSON. If you're using gRPC, it can be protocol buffer binary format. In Airframe RPC, we are going to use MessagePack, which will be explained later. We also need an interface language, RPC, REST API, or ProtocolBuffers RPC, or Scala. Number 4, we also need a client-server code implementation, which is often generated from the RPC interface. For data serialization, we created airframe-codec, which is a MessagePack-Based Object Serialization. So this basically receives the object in Scala, then translate it into a MessagePack binary format. Then for the server side, it unpacks the MessagePack data into the original Scala object form so that we can deserialize object data through MessagePack format. MessagePack format is a sort of compact binary format that is compatible with JSON. So for example, you will find this JSON data, which is written in 27 bytes. If we translate this JSON data into MessagePack, it can be represented just by using 18 bytes. So it's a compact JSON format. And we defined various predefined codecs for Scala primitive types, collection types, Java-specific types, so that we can encode arbitrary Scala object into MessagePack format. Then by combining various codecs, we can also serialize more complex Scala objects. For example, this case class A has 3 parameters, port, name, and timeout. By combining codecs for individual parameter types like integer codec, string codec, double codec, we can create a complex object serializer that translates convert this object data into MessagePack format and vice versa. The usage is quite simple. You need to call message codec of type A. Then by using this codec, you can read the JSON data like this to create a model class object. And actually, the magic behind this message codec of A code is by using compile time macros, we are inspecting the object parameters, names, and their types. We are using actually different implementation between Scala 2 and Scala 3 because compile time macros implementation became totally different between Scala 2 and Scala 3. But actually, it's all the Scala 3 support is almost complete. So we can use this both for Scala 2 and Scala 3. The other problem is, we not only MessagePack, we want to use YAML format, JDBC result set, JSON data. So actually, we have many data objects we need to support. Even for taking a JSON, there are a lot of existing libraries for passing JSON, mapping JSON data into object like Sassy, JSON4S, PlayJSON, Jackson from Java world. Sometimes it's used in various frameworks, but it's really complex to learn the individual usage. So our approach here is simplify what we need to learn. So we are trying to convert all of the possible data types like YAML into MessagePack, JDBC wizard set. It's also converted into MessagePack. JSON is also converted into MessagePack so that we can reuse the same object serializer deserializer library, which is airframe-codec for supporting various data type format. And actually, by using this conversion, MessagePack will work as a universal data format between the various data types. Actually, not only MessagePack, Airframe RPC can use JSON for making RPC calls. We can also use Airframe RPC and airframe-codec for serializing function call requests. And the basic idea is serializing function call arguments as Scala's map from function argument name to argument values. If you have this hello method with person on the message of argument, and the person is a case class like this, then you need to create a map element like this, person to person object, message to some string. Then we are going to serialize this map object into MessagePack format by using airframe-codec. After serializing function arguments, we need to send this data through the network HTTP method. Then we are going to use HTTP post method. The path with access path is defined like package name dot class name hello API v1.myby service followed by /hello. Then this mapping will be automatically generated once you define Scala to it in your PC. Then content body will be just a serialized function call argument. Then, what you need to implement server-side application is very simple. So once you have a My Service RPC interface written in Scala, you just need to extend it to implement, provide your own Scala implementation of the interface. In this example, just producing a new Scala, a new string, just by writing Scala code. It's very simple. Interesting thing about Airframe RPC is its backend server and clients are pluggable. Like you can use, for example, Finagle both for server and client side. You can also use gRPC as a backend implementation of this RPC interface. Then if you want to use Finagle backend server, Finagle is actually a Twitter's high-performance HTTP server implementation written in Scala. This is useful for building HTTP1-based service, which is accessible from most web browsers. Then you need to define a router definition, which is the RPC service implementation. Then for launching Finagle server, you need to go finagle.server with router. Then you are going to add the router you just created. Then by specifying code and just start the server. So that's it. So then you can start a Finagle server with RPC support in this amount of code. If you want to use gRPC backend, the approach is almost the same. You define an RPC interface in Scala, which just define, for example, say hello method. Then you provide its actual concrete implementation. Then the router will add a great API's implementation. Then you can start the RPC server just like Finagle server. As you notice, there's no protocol buffer file definition here. You're only seeing Scala code. So there's no difficulty. If you know Scala, you can just write Scala even for building gRPC-based services. Here is a quick comparison between HTTP1-based service and gRPC-based HTTP2 services. This chart shows how many RPC requests you can make per second. Blue bar shows the synchronous RPC calls, which means you are going to make RPC call one by one. But red bar shows asynchronous RPC call. So you can call as many RPC calls as possible, then getting a response from the server in a synchronous manner. Then if you are using Finagle HTTP1, you can make almost 16,000 RPC calls per second But if you use the RPC backend, you can make 40,000 to 50,000 RPC calls. So it's a significant difference. The three here we compare three frameworks: Scala PB Airframe with gRPC backend, gRPC Java. Actually, gRPC Java is used for both for Airframe RPC, Scala PB, the backend. So actually, we are introducing Scala as an intermediate object. So there are several overheads of using Scala PB or Airframe RPC, but the difference is not so significant. Even for Scala PB or Airframe gRPC, we can make 40,000 RPC calls per second. This is actually sufficient performance for web services. For whom you may interested, simply using HTTP2 or over Finagle didn't show much improvement because protocol itself is not the key. Rather, implementation of how to use HTTP2 was the biggest performance factor. Especially gRPC Java is trying to multiplex multiple RPC requests into a single connection. So that produced this huge performance difference. If you want to see the overhead, you can find Scala future or mapping ProtocolBuffer to Scala case classes has some overhead in Scala PB. But this overhead is almost negligible in VR application services. This is actually a little bit advanced topic, but actually gRPC itself is data format agnostic framework, so you don't need to use protocol buffers. You can use JSON message pack instead. For example, to do so, you need to extend to points in gRPC. You need to provide your own method descriptor, which define gRPC endpoints corresponding to your Scala functions, or you need to register your custom data marshals. Marshals are actually encoding, decoding your HTTP request responses. In Airframe RPC, we are embedding Airframe codec here. Here. This is just this code is very simple, but you need to define method descriptor for individual RPC endpoints, and writing this code every time is very challenging task. So we created sbt-airframe plugin for generating RPC clients from your RPC interface. For example, sbt-airframe plugin reads this RPC interface marked with RPC annotation. So RPC annotation itself does almost nothing. It's just a marker for finding RPC endpoints for you from your class path. Then sbt-airframe generates RPC clients for the targeted backend like Scala JVM or Scala.js or gRPC. Different code generator is used for individual backend types. We can also generate Open API spec schema for creating rich API documentation. Once you create an Open API YAML spec, then you can use Swagger editor for creating a rich API documentation that can be visible from web browsers. But and also if you want to support other programming language like Python, then it should be possible to generate cross-language RPC clients because Airframe RPC supports JSON format as well. You can make a simple JSON RPC call to the server, then getting JSON response. But you don't always need to generate OpenAPI because RPC interface is already written in Scala. So simply adding a comment to your Scala code can be a good API documentation. So actually, Scala can be a central place of defining RPC. Then here's a nutshell of what we have seen so far. So you define RPC interface just by using Scala. The sbt-airframe plugin generates a service synchronized client. Then you just need to make a RPC call using the generated client my service hello method, which accepts the person case class object, then you get a response from the server. The code is quite simple, just plain Scala, but behind the scene, we need to do many things like serializing Scala classes into MessagePack, server-client interaction using Finagle or gRPC. But yeah, that's it. So by using Airframe RPC or Airframe RX, you can enable Scala-oriented development with Airframe. So you can define RPC interface just by using Scala. You can generate client-side code. You just need to implement this interface for building server-side applications. So yeah, today Martin Odarsky mentioned really good things. You only should be able to learn only one language just by using Scala. Then actually Airframe RPC is trying to achieve this goal. You should be only use Scala, and you should only learn Scala. Then you should be able to write various applications, including front-end application, back-end application, without thinking about REST protocol, ProtocolBuffers, or other front-end framework at the beginning. You should be able to use, for example, more advanced front-end framework in later phase if you really necessary, for example, generating web application for code for mobile devices or more specialized devices. But just for starting front-end development and back-end development, you should not think about too much things. You should be able to just use Scala for writing your own applications. And you can find more example codes on GitHub repository of the Airframe. And there is an example folder. You can find more concrete example, including build SBT setting or how to interact JS application and server-side application using Finagle or gRPC. Okay, so that's the last slide. Okay, so I think we should move to Q&A.
All right. Well, thank you so much for your talk. And now it is time to jump into our Q&A. So let's see what questions we have. All right. So while you mentioned Slinky Scala tags, I wonder how do you compare the Scala.js side from Airframe to Laminar?
Oh, yeah, it's a really interesting question. The Scala tags are really old project, which was exist almost when Scala.js was released. So it's sort of all these, but yeah, Laminar is, I think it's a relatively new project. Actually, I haven't compared in details about Laminar, and actually, but as long as I read the Laminar's documentation, the concept is very similar to using single block for enclosing DOM elements or supporting cancellation. So actually, yeah, you can use your preferred Scala.js libraries. And actually, and Airframe RPC can be a bridge between arbitrary Scala.js applications. So yeah, server-side applications. Yeah, but yeah, there are many approaches exist.
All right, great. Let's go to the next question. And let's see. Given that Airframe depends on macros to use the RPC APIs, have you analyzed the challenges to support Scala 3?
Yeah, actually, the major challenge is how to use tasty reader for, actually, for scanning RPC interface and defining jar files, we need to know, we need to convert class files into Scala's interface definition. For doing so, we need to use tasty reader for Scala 3. Actually, then several things we need to overcome. We don't know how to find tasty file. Where is tasty files located inside jar for corresponding to individual class files annotated with RPC markers. So this kind of simple thing is not well designed at the current tested reader. So we may need some improvement in the Scala 3 side. Actually, yeah, how to use tested reader is still challenging part. I know it's working to some extent, but if we run multiple tested readers concurrently, it shows some errors. So I hit this error before.
All right. Well, I think that's the last question we have. So Taro, thank you so much for your talk today, and thank you for joining us here at ScalaCon.